Happy 2025, everybody. Hello, good morning, good afternoon, good evening, everybody, wherever you might be. It is my great pleasure to introduce my fellow co-organizer and friend and colleague and collaborator, TOMASZ from the University of Warsaw, who will speak about Clifford-Dirac quantization of the Rham complex. It's all yours. Take it away.
Thank you. So I will start with some controversial subject, some problem which arise in non-commutative geometry in the context of homological computations with the use of the Clifford algebras, Dirac operators, and all this stuff. So let's assume for simplicity that all our objects are algebraic. It's not necessary, but it makes all considerations much easier. So assume that A is some smooth K algebra over some field. You can think about complex numbers. And this algebra is smooth, which means that the module of other differentials, algebraic differential forms spanned by this algebra A, is phi as the projective module over A. Okay? And then we can consider a non-degenerate symmetric A bilinear form. You can think about this form, which is denoted by pi here, as in a sense, inverse of the Riemann metric. Okay? Having this, we can generate from this non-degenerate symmetric form on this module of differentials, we can generate the Clifford algebra. This Clifford algebra has some structure, special structure, which is called ascending filter Z2 graded algebra. If you remember the presentation of the Clifford algebra, when we divide the tensor power algebra by the ideal generated by relations, these relations are quadratic, but non-homogeneous. Okay? This non-homogeneity implies that this Clifford algebra is it's not a Z-graded algebra, as the tensor algebra was. And this introduces some problems with interpretation of some things you would like to do with the Clifford algebra and Dirac operator. This algebra sometimes has a distinguished module. It's called the module of spinors, which is a Z2 graded Clifford module of this Z2 graded algebra. And using the Levi-Shigeta connection defined by this non-degenerate 4 pi, we can construct the Dirac operator, defined as the composite of the following three maps. So first, we are using this connection, this Levi-Shigeta connection. Then to the first slot, we apply this Clifford multiplication, this universal map from this quadratic module to its Clifford algebra. And then we are using the module structure in spinors with respect to multiplication by elements of the Clifford algebra.
Sorry, just a bit question. Your A is still commutative, right?
A is commutative. A is commutative.
I don't see. Yes, smooth commutative, of course. Yes, yes.
So the point is that when you try to make theory non-commutative, you first have to understand this commutative case. Sometimes people are doing some illegal things, thinking that they are developing Rice theorem. I will say something about this. in the context of Dirac operator, there's an important relation between this zero-graded and ascending filtered algebra and the differential graded algebra to Z-graded, which is the universal differential calculus on this algebra A. And then we have some distinguished map from omega AK. It was some,
It still is. No, but this one which you get disappeared.
oh, okay. So we have this universal differential calculus, which is non-commutative in nature. So please know the difference between the kind of differentials, which are commutative, and this associative algebra, which is integrated. Then, in the Dirac operator of degree 1, we can associate with a couple of elements of the algebra, which provides a representation of a generic element, simple tensor element in this universal differential calculus. We can map it into such an expression. When it goes to the operator of multiplication by an element A of spinors, and every universal differential of an element goes to the commutator with the Dirac operator. So this is a very well-known expression, it's very important, appears in many important formulas, for instance, in the common formula for the function character spectral triple, when paired with some Schmidt trace applied to some product of this element with some pseudo-differential operator of the order -n, gives you some invariant, which is called the function character of the spectral triple, regarded as a multilinear function of these elements of the algebra. And then, although the image of this map sits in linear operators on the module of spinor, the image of this map sits in fact in something much smaller, which can be identified with the Clifford algebra. So this map can be decomposed through first the map from the universal calculus to the Clifford algebra by the very, very similar formula, when the image of every universal differential of any element of the algebra A is replaced by the operator of Clifford multiplication by the differential of this element of this algebra. And then
Tomek,
yes.
Can I ask?
Yes.
Can you hear me? It's Ludwig.
Yes,
Hi,
we can
Tomek.
hear you. Now we can even see you.
Okay, Tomek. So the map sends the exterior, I mean, the universal differential of A1 and to some commutators, but you write tau depending only on A0, A1, AN. So it doesn't depend. It depends on, I mean, not really on delta of A, but on A itself. You say yes.
On what? Doesn't depend on what?
Well, the formula
Yes.
sends delta of A1 to Baba commutator of D with A1, but the tau is defined on A1 itself, so it's well defined.
Yes.
According to you.
Yes, but,
okay.
but it is through this map. First, we are sending this universal element to some operator like element like this. And
I know, which is perfect, but in the next formula, you have super trace of, I mean, it's okay, right-hand side is almost the same, but left-hand side, there is no differential of A1, but just A1 itself. So it is well defined on the
I cannot see any differential on the left-hand side.
Well, that's exactly his complaint.
That's what I complain.
But why? Why would you expect?
Because you have to define this well defined on A1, not only on del of A1.
No. So this is defined not on the level of this universal differential calculus. This is defined as an element, which is a co-cycle, Hawking co-cycle on the algebra A itself.
So it's on Hawking co-cycles, okay.
Yes.
And in the last equation, you don't say on or how it's defined on A1. It's also on Hawking cocycle, but you write it omega dot A over K. You don't write it as the last equation, okay? The last equation is similar to the first equation, but the middle equation is different.
Are you talking about this equation or about what?
No, there are three equations on your blackboard, okay? The first and third.
No, there are only one equation.
There's only one equation. Yeah.
Okay, there are three maps. Okay.
Okay.
There are three maps. First and third are quite similar. Second is different.
Yeah.
The middle one is different. The last one is also defined on Hochschild cocycles or
no.
on omega.
It is this map decomposed into first. Going to the Clifford algebra, of course, this is an operator of degree order 1, which means that the commutator of D and A1 is an operator of the Clifford multiplication by the differential of this element D, A1. Okay?
Okay, but is it well defined as the middle one, the middle map, also on Hochschild cocycle?
And then it is followed by the injective Clifford module structure map.
Okay. Okay.
So these are operators. Okay? These are elements of the Clifford algebra, which you can tautologically define in terms of Clifford multiplication. Okay?
Okay. Go on. Thanks.
Good. Okay. So this map from the differential calculus to the Clifford algebra is very far from being any kind of isomorphism, of course. It's subjective. Okay? However, it has some parallel. And this parallel plays a role when you try to make this map a map compatible with the differential on this universal differential calculus.
Yes.
Okay? There is some obstruction for descending this differential to this Clifford algebra. How we can produce some tautological obstruction? Take some element here whose image is 0 in Clifford algebra, okay? And then try to compute its differential here. Then, if this was differential graded algebra map, then this differential will go to there to some kind of differential applied to the image of this element itself. Okay? But it turns out that there are some elements in this differential, universal differential calculus, which are in the kernel of this map, whose universal differentials go to something non-zero. Okay? So, to have this map, a morphism of differential graded algebras, we have to divide by the image of all such elements which are 0 under this map and images of whose differential are arbitrary. Okay? And in this way, it's a very cheap way to achieve a morphism in the category of differential graded algebras. Okay?
Tomek, just about notation. Can I ask again? Sorry, again, Ludwig. So you write in third line from down, okay? Delta of name bracket, E bullet, -1, left bracket, and the bottom.
Okay. Oh, sorry. So this should be a square bracket. when
Okay.
in many places.
By this you mean that, Tomek, by this you mean that you take I bullet -1, so just one less index of the.
Yes, it's a shift.
Thank you.
In
Thank you.
In the degree.
Thank you.
Okay. Imagine in this Clifford algebra of all such elements sitting in the which are images of universal differentials or elements in the kernel of this map is called the great idea of Junk forms. Okay, so this is the subspace idea, which is in this different algebra, which is responsible for the obstruction for Eastman being extended to the differential grades algebra map. Okay. So what is the strategy? I stressed the word tautological. So in a sense, it was the history of a failure. And around this failure, we are going to create some interesting story. Okay? And human imagination produces many objects, like for instance, well-known snapdragonfly or red and butterfly from Lewis Carroll. Alice the Looking Glass. Okay. Now, what is the problem with junk forms? The problem is that people tend to see in expressions related to this Clifford algebra spanned by differential forms, they want to see something which is related to differential calculus. The best possible situation would be if this was related to the Rham complex, because the Rham complex is a basic structure, basic complex built with differential forms. Okay? But if you try to think philosophically or mathematically, what do we need for all this stuff about the junk forms? We have to answer the following question. One would like to have a structure of a complex on such a quotient with the differentially graded algebra of universal forms, first of all. Okay? And my answer is that people are hypnotized by the Rham calculus. And when they see something which is even tangentially related to this, they want to extend what they would like to have in this situation. Okay? And I should warn you that in some literature, mostly produced by some mathematical physicists, some authors claim an isomorphism between this quotient algebra and the algebra of differential forms. Some of them are so sure about the truthfulness of this hypothesis that they attribute it to Noncommutative, okay? Who, up to my knowledge, never said this. Okay? But it is wrong. This is that one. So what do we cut of that? So let's assume that our field is a field of complex numbers, who is inverted in there. And let's assume about our algebra that elements which are values of this symmetric form on differentials of functions generate an improper ideal in A. Improper ideal means that this ideal contains the unit of this algebra. Okay? First of all, there are plenty of such examples. Having this module of differential forms non-trivial. For instance, you could take the algebra of functions on plane or even on the line. Okay, and you can introduce star product between differential forms in such a way that the coordinate x has a differential of value of this form on this differential equal to 1. So it corresponds to Euclidean quadratic form. Okay? So this is real. But of course, this algebra has a non-trivial module of differential forms and even all these differential calculus, commutative differential calculus. Okay. Let's take such elements in this universal differential calculus and try to serve the image under the map we're talking about. So what is the image of this? The image is the commutator between the element of the algebra and multiplication by the differential of this A prime. Okay, which is 0, of course, because functions form essential subalgebra in Clifford algebra. Okay? But let's take the universal differential applied to this element, such elements. Okay? What do we have? We obtain the anti-commutator of two differentials of this element, which under our map go to such anti-commutators in Clifford algebra. But what is it, anti-commutator? By the relation defined in the Clifford algebra, it is this element. Okay. So, if such element spans the unit of the algebra A, and since the unit of the algebra A is also a unit of the Clifford algebra by the canonical map, we see that this idea of giant forms is involved, which means that the quotient of the Clifford algebra divided by giant forms is trivial. Because you have, although the algebra of differential forms is not trivial. Okay? So, therefore, I said that this conjecture is flat and wrong. Okay. So, you could be surprised.
Like, can I ask you a question?
Yes. Yes, please.
So, yes, I mean, does it apply to this argument? Does it apply to the case, like for the manifold case, even?
Yes, yes, of course. Yeah. So what is the source of the confusion? What people? Where's the point? Could you pinpoint the place in all these considerations, which are many in the literature? People are confusing two things. They are starting with the differential graded algebra of universal forms, and they are trying to think about the Clifford algebra as a differential graded Z-graded algebra, which is wrong, because it's not. Okay? Okay.
So, okay, why this quotient is 0? I don't.
Sorry?
Because
Why this quotient that is Clifford?
It is an improper idea containing a unit. And by the definition of an idea. Okay? So, it's astonishing how thick business could be developed around this confusion.
Okay.
Tomek, again, can you come back to the previous? Just for maybe you said this at the beginning, but I missed it. So, Clifford algebra is Z modulo 2Z graded, right?
Yes,
And you also add the adjective ascending filtered, which is more than just
yes,
that. Okay.
yes, yes.
And instead differential forms?
It's a positive ascending filtration compatible with Z2 gradient.
Okay.
Great.
And what about differential forms, omega dot?
It's a Z graded differential graded algebra.
Okay. And the problem between these different gradings is the problem that you say that
Yes.
that's the origin of the problem,
Yes.
right? Okay.
But this is the core of the problem. So probably people are used to use some identification between the Clifford algebra and its associated gradient, which is the exterior algebra. And if our exterior algebra some additional gradient, which is a Z gradient, although the isomorphic is only an isomorphic of Z2 graded algebras. Okay? Okay. So all this business is like balancing and yield on the tip of your nose. Okay. Besides this other example, you do have some more fundamental objections to all this ideology. So first objection is like this. We know that the periodic cyclic homology is related to the Rham homology, but in a much more simple and more natural way, without any need of the Dirac operator. So if you are employing this Clifford algebra of differential forms, next to expecting some relation with the Rham homology, why? Because you can do it without a Dirac operator. Okay. And the second point, which is the main point of this talk, is that actually there is a relation between this Clifford algebra equivalent to the Dirac operator and the Rham complex, which is much simpler than what was written and more natural. And the problem of Rham forms doesn't appear at all. Okay. Okay. So what's my problem here? My gut feeling is that it's the right approach, but you can discuss. So the first step in explaining this relation between this Clifford algebra and this the Rham complex is based on this identification I said. Okay? That you can speak about the associated gradient of a filtered algebra. So provided this filtered algebra has this filtration compatible in an appropriate sense with the Z2 gradation, its associated gradient is equal to the Z gradient. Okay? And then we have, for instance, in the case of the Clifford algebra, we have this associated gradient, which is orthogonal to the algebra of different forms. So you should be warned that we don't have a map between Clifford algebra and this construction modifies elements of this Clifford algebra a lot. Okay? So this is not of the map which was expected before.
Can you say again what is this G dot doing to Clifford?
Gradient.
It's just gradient.
If you have a filtration, you can take consecutive factors
Okay.
of the higher filtration divided by the filtration if you update the cost. Okay? So this is by definition, this thing is C2 gradient. Okay? But because of compatibility of this filtration with the Z2 gradation, it gains some additional property, heat gradient. Okay, I will explain what are these conditions. Okay, so this nuance about this compatibility between this filtration and this Z2 gradient is contained in the definition. So having an ascending filter algebra, as before, we want to find the conditions guaranteeing that the gradient associated is equivalent with the Z filtration, Z gradation. Okay? Okay, so having Z2 graded algebra with an ascending filtration, we call it Z2 graded ascending filter. First of all, ascending filter, that's an algebra, nothing new. The filtration respects the Z2 gradient, which means that these consecutive containments are fulfilled degree-wise, Z2 degree-wise, which is natural. But this must satisfy some additional conditions. Then, if you go from even filtration to odd filtration, then you can add only odd forms. On even forms, nothing is added. Okay? And similarly, if you have this odd filtration, same holds for these even elements. So even elements cannot come from something of this odd filtration. Okay? And then the simple consequence of this assumption is that the odd graded part of even elements is zero, and even filtrated the graded part of elements is zero. Which means that the associated gradient is equal to the canonical Z filtration, which is compatible with the initial Z2 gradient. So that if you take the image and you obtain something which is Z2 gradient, okay? But applying to this gradient coming from this filtration, you obtain a C gradation for this element whose reduction modulo 2 coincides with the initial Z2 gradation of this initial element. Okay? So this is a new concept. Okay. So on the level of gradient associated algebras, we have what we want to do. Okay? But then we have to use some differential calculus on this Clifford algebra. First of all, to define the Clifford, the Dirac operator in terms of the Levi-Civita connection and then this Clifford multiplication. So, first important step is to change the notion of the Levi-Civita connection to a notion of some constant cosine. Okay? As in this theorem. If we have, or maybe I will start explaining from this point. If you have a differential form, omega I, we can make from this one form a vector field by applying the isomorphism induced by the non-degenerate quadratic form on differential forms. Okay, and then we can apply to this the operator. We can fill with this the slot of the operator of absolute derivative with respect to the Levitt-Civita connection along this vector. And having some monomial consisting of many such one-forms, you can construct an operator on the Clifford algebra obtained by this formula. At first, it doesn't look that this is even well-defined. Something to do here to first define that this is well-defined. But some portion of the content of this theorem is that indeed it is well-defined. And then we can apply this element. Instead of monomial, we can put here any element of the Clifford algebra. And for two elements of the Clifford algebra, x and y, we can apply such a combination with use of this operator here. Okay. It turns out that, first of all, it's a well-defined and then normalized two-cycle on the Clifford algebra, which means that it satisfies the system equations. So being normalized means that evaluated on the unit of the Clifford algebra is 0 in both slots. And second, it satisfies some graded version of the complete supercycle condition. Okay? So now we are starting to think about this Levitt-Civita connection on this Clifford algebra as a completely different animal.
Tomasz, can you remind me, this pi, you get it from where?
From this non-degenerate quadratic form on differential forms.
Yes, I think pi is a bilinear, like it's a bilinear form, right? So y here is only applied to omega I. This.
Not here.
Say it again, please.
Could you repeat it?
So pi is a bilinear form on this omega 1.
Yeah, and this form is non-degenerate.
So then what does it mean pi of omega I? I mean,
There should be musical notation there, but it's okay.
Yes. Okay, so I'm identifying here this quadratic form and the map between differential forms and vector fields induced by this. It's like in Lewis theorem. Okay?
Okay, so here, so you need a notion.
So Hilbert spaces, you always write vectors of a Hilbert space, but sometimes they are not. Okay, there are bra and pets. Okay, and pets, they are dual to the bra, and the duality is given by this scalar product. So in the same vein, I'm identifying.
That was actually clear for me, but what I'm confused by is this comes as an input data from where? Where did you assume that you have such a non-degenerate form?
It's the beginning of everything. It's an assumption.
Okay.
So maybe in a few weeks, maybe months, I can show origins of non-degenerate symmetric form on differentials, but not this time. It's an assumption.
In order to speak about Clifford algebra,
Riemannian
must start from bilinear form.
Sorry?
In order to speak about Clifford algebra, Tomek must start from some bilinear form, okay?
Oh.
Okay, it's from Clifford. That's sorry, just you should have said Clifford, okay.
Yes. Okay. So I hope this is clear.
So here we assume a Levitt-Civita connection at the beginning, right? So a Levitt-Civita connection at
No, we are not assuming Levitt-Civita connection can be computed unambiguously from this non-degenerate form.
Yeah.
Okay?
But he is still commutative. He's still commutative.
Yeah. It's not an additional datum.
Yeah.
It's in the package.
Yes.
Once you choose
Pi.
pi, you have all this package.
Yeah.
Oh, of course, this spin structure. Okay. This is the second. But look, on the level of the Clifford algebra, you can ignore this spin structure, which is also very pleasant thing. Spinors do not play a role here.
Tomek, can I ask? Tomek,
Yes.
so in principle, this could be Clifford algebra representation on differential forms itself.
I will be careful because, of course, Clifford algebra acts on itself.
Yes.
Okay.
Yes.
But if you want to use this fact to obtain the action of the Clifford algebra on differential forms, you could use some non-algebraic, being not an algebra map, linear isomorphism between this associated graded algebra and this filtered algebra. It's
Yes,
like splitting this filtration.
Okay.
Which you can do using orthogonality property if you are doing everything over reals or over complex numbers, when you have positivity and so on and so forth. But otherwise, this splitting could be implemented by some operators of internal contraction of the vector field with a differential form. You can extend them to these operators to Clifford algebra, and it's quite and this identification is quite complicated. Okay. So this is not an algebra map. This identification of differential forms with the Clifford algebra.
It's a vector map, linear space map only. Okay,
yes,
map.
it's only linear space map.
Tomek, but once more, just to the question of Young, if we have time, of course.
Yes.
I just want to understand the meaning of the first line, actually, first sentence. So you have Levi-Civita connection on Clifford algebra? That's what you say here? Or you want to say that you will get it from this Levi-Civita concept?
So Levi-Civita connection preserves this idea, this object.
Okay.
And acts as a derivation. If you fill this Levi-Civita connection with a vector field, it's a derivation of the Clifford algebra.
Okay, but Young just asked about it. So Levi-Civita connection input here, yeah? It's assumption that you have it. Or you want to construct it from something?
It comes together with this pi.
Okay.
Okay, it's always there.
Okay, thanks.
It's canonically related to this pi. Okay, so this is my understanding of this connection on the Clifford algebra. It's a normalized cosine to cosine. And now we can speak about the Dirac operator. So similarly as on spinors, you can construct the following canonical composites of these maps, and then you obtain the Clifford, the Dirac operator on the Clifford algebra itself. Okay? And then this is a map from the Clifford algebra of degree 1. It's an odd operator, increasing filtration by 1. So you can see that although we are in objects which are graded, sometimes I'm writing +1, sometimes I'm writing -1 in the context of filtered Z2 graded objects. Because sometimes these odd elements not only are odd, but they also increase filtration by 1. And some of them, like this operator, they decrease this filtration by 1. So omission of this form here and putting this omega I as an argument of this derivation of order 0 means that this symbol is an operator which is odd and decreasing the bilinear, increasing the sum of equations by 1. Okay. Okay. So this Dirac operator itself on the Clifford algebra can be regarded as a normalized function, one cocaine, which is odd and included by 1. And then we have still these things are related. How? This Levi-Civita cycle beta is the co-boundary of the Dirac operator, which means it satisfies the following Z2 graded generalization of being a condition of being constant about. Okay? I think it's quite interesting. So, why this is so interesting? Because if you remember from spectral geometry, the Dirac operator is a primary data.
Yes.
Okay? And everything should come from this. Okay? So you see, in a sense, some repetition of this principle. Okay? Why? In this direction. Why Dirac is more important than the Levi-Civita connection from this point of view? Because beta is a co-binary, which means that you can fill it with this Dirac operator and you obtain this Levi-Civita. Okay? But if you have this Levi-Civita and you would like to ask what is this Dirac operator, you see that this Dirac operator for fixed beta is not unique. Is defined up to a constant plus side, cosine. Okay? So this is important direction from Dirac to Levi-Civita. Although at the beginning we first used this Levi-Civita and then we produce from this Dirac operator. But it's an accident of history. Okay?
Oh, yes, because when we axiomatize Dirac and we don't care about how we get it into the classical case, okay.
So now, what about the Rham differential? So there is also property of this gradient associative operation.
So Thomas,
Yes.
so okay, so can you go back to the previous slides? So okay, so here we know that the Levi-Civita is something unique. I mean, in the Dirac you still use Levi-Civita. I don't understand. So it's like, so what's so in your definition of this Dirac, so you have also assumed you have this disconnection map in the first, right? So
Yeah, so at the beginning we started from the metric, the Levi-Civita connection, the Clifford participation, okay, and then we took up the Dirac operator.
yeah.
But from this homological point of view, the relation is opposite. The Dirac is primary, and the Levi-Civita connection is secondary. Okay.
No, you are saying something like you can give some axioms about this Dirac operator, which then using axioms you can reproduce the Levi-Civita connection. Is that what you are saying in here?
Yeah. So you will see this point of view developed further.
Tomek,
Okay.
can I ask again the last line, the last equation? Okay, beta decreases by 1, the grade, right?
Yes.
Decreases by 1. So it is difference to kind of 2, but the commutator decreases, I mean, this left hand side combination decreases again by 2. That's what you want to say. This
Right. This is an important point. Yes, it's a very good observation. So T increases by 1, but this combination decreases by 1.
Okay, that's what it. Okay, thanks.
So there's some shift by 2, which is responsive, which is compatible with all this nuance about the relationship between this filtration and grading, little grading. Okay. So, we then complete this Levi-Civita connection using the Dirac operator as well. What about the Rham differential? Okay. Now it's very simple. Because the Levi-Civita connection is first of all torsion-free. And if we have a torsion-free connection, then we have a formula expressing the exterior derivative of a differential form in terms of the Levi-Civita connection applied to this form, the differential form. Okay? So sorry, Andrzej, but the condition of being torsion-free now is essential. So if you want to try to ask anything about torsion, the role played by torsion, it's an question.
No, but I will make a comment at the end, okay? And Andrzej perhaps also.
Okay. So first of all, we know that Levi-Civita connection is torsion-free, and the resulting Dirac operator on the Clifford algebra is odd and increasing the filtration by 1. If you combine this fact, then you can prove that the Dirac operator on Cliff induces the Rham differential on the associated gradient algebra, which makes differential terms at the Rham complex. Okay? So I think this is probably right way of thinking about this relation between Clifford algebra and the Rham complex. Okay. And then let's try to think about this operation as kind of deformation. When we think about this Clifford algebra together with the Dirac operator, it's a kind of deformation quantization of the Rham complex. Okay? And there is some device which is called the Riesz algebra, which can produce some one-parameter family. It is an analog of this formal deformation you are familiar with in the context of deformation quantization. Okay? So in this case, it's something which is called the Riesz algebra, defining defines as follows. So we start with ascending filter C2 graded algebra T dot.
It could have been a C star.
It will be, of course, Clifford, but this is general.
F is an ideal or something? What is F?
Filtration.
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 So this kind of filtration is different from other filtration defined by ideals, because those are usually decreasing filtration. Okay? This is an ascending filtration, it's increasing. Okay? Opposite. So given such an ascending filters to our graded algebra C, we can cook up T and C2 by graded subalgebra of the following form. So we have a direct sum of all filtrations of C multiplied by the power of an inverted indeterminate of degree 2. Okay? And then in this C2 bi-graded algebra, this is such a subalgebra. And this subalgebra is, by analogy with this construction, you probably know, with the theory of adding theory, adding condition, the deformation of the normal cone, all this stuff. So this is an algebra. This, therefore, I call it also Riesz algebra.
So can you just make sure my understanding about this notation? So you take this this algebra C, and then you make it the Rham polynomials, right? And then this Riesz algebra, you require this coefficient of this t to the power n is belongs to this nth iteration of this algebra, right? So that's the meaning of this Riesz algebra.
Yeah. So this by grading accounts for two things. So first of all, C dot is Z2 graded itself. Okay? But then we have here something coming from this iteration and something coming from this degree 2 of this variable 2, variable t. So, okay?
Mm-hmm.
And how important it is here that it's Z2 and not some other, say, finite group?
Well, you could try. You could have some integral counterpart of this, maybe. For sake of knowledge, you can think with how simple. But Z2 is good.
But you say you're gonna use it as some sort of blow up.
In a sense, in the case of the idea,
Yes.
it would be like a blow-up of an idea.
Yeah.
But for this descending equation. For ascending equation, there is no such.
Yeah. Okay.
So the sort of this kind of equation comes from the representation theory. For example, enveloping algebra, 3D algebra, is equivalent to the canonical extended equation by the number of elements which are using monomials. Elements of the algebra using monomials. In differential operators, you have an extended equation by the order of a differential operator. Okay, this is ascending equation. Okay? In a sense, all these questions are dual to this question about this adding equation, because this duality between, for instance, nilpotence and infinitesimal, okay, in Grothendieck theory, okay, of locality of speeds.
So okay, just about notation. So this Riesz algebra is bi-graded as a, so it's right. So that
yes, it's bi-graded.
So and then this degree 2 means which group?
Yes, that's my question is also of degree 2 refers to what, Tomek?
The block.
Maybe I forgot to. Yes, maybe I should write here 2 dots. Okay, but then yes, this dot which is here corresponds to this dot which was present there. But there is another grading coming from this direct sum and labeling these pieces by n. Okay? So in fact, here you have 2 gradings combined.
So the Riesz algebra you want to be Z graded.
It is Z graded.
It is Z graded. It's Z2 by graded.
Yeah.
Okay? Z grading comes from the filtration. Z2 grading comes from the original Z2 grading.
Exactly.
But you are not taking quotient of this, but you have a filtration, but you are not taking the quotient of it.
No.
No. It's a direct sum, no quotients. But if you're asked what about quotients, I can explain. So first of all, since zero filtration is contained in the first filtration, and zero filtration contains 1, then after passing to this direct sum, there is a shift by t. And after this shift by t, 1 becomes t, sitting in the first filtration, in a sense, okay? After multiplying by powers of t. Therefore, and then we can consider specialization of this t, giving this variable t some value in the field K. Okay? So for example, if you take the value t equal to 0, which means that we are divided by an ideal generated by this element t, we obtain the graded associated algebra of this Z2 graded filter algebra. Okay? But if we take any invertible element of the field, okay, and then specialize, which means reduced by the ideal generated by this difference, this for any invertible value t is isomorphic with this filter algebra we started with. Okay? So for instance, if T was a Clifford algebra, then the central fiber of this deformation, when you can imagine this. Where is this? Yes.
You know, because you switched into hand, you have to press.
Can I do this one once? Okay. Every time I have to switch. No.
This is strange. I don't understand why.
Very strange. So this is it. Oh, no.
Try the black one. Try the black one. No.
So this is 0. Okay. So here we have T. This is 0, okay?
This red blob is 0.
And this is T.
Read what you're doing, Thomas. You should read what you're doing. Yeah, we are pressing something and. Try the black one.
Right.
Yeah.
So that this will be, that will be better. So T invertible, which means that it's different. Okay. So for all values T invertible in the field K, in this one parameter family, we have this filter algebra. Okay. But the central fiber of this deformation is the associated graded of this filter algebra. Okay. So in a sense, it's a specialization or degeneration of this filter algebra to its associated gradient. So, if you think about the Clifford algebra, we obtain the similar picture. When here you have the Clifford algebra everywhere, degenerating to this algebra of differential forms. Okay? Okay. After applying this operation of the risk deformation to the Clifford algebra, we can extend the Dirac operator to this risk algebra, obtaining some family of deformations of this complex. Okay? And we call this resulting deformation the Clifford quantization, when we ignore the question of the Dirac operator and the Rham differential, and if we are interested in the relation between the Dirac operator and this the Rham differential. Okay. So now, if I set quantization, so knowing that we have in this limit, in the classical limit, something classical, you could ask, okay, we know this classical limit, but what is the quasi-classical limit? So what is the story about this quasi-classical limit? So if you want the parameter deformation, you can speak about the limit and the first derivative of this deformation. Okay? So probably you are familiar with the situation when we have a commutative associative algebra, and we start deforming according to some one parameter family, deforming this commutative multiplication to an associative one. Okay? And then, this is probably a folk knowledge, but you can compute it. You can check it. I couldn't find the reference. If you have a one parameter deformation of a commutative multiplication to something which is associative, there is first order coefficient after anti-symmetrization, which means anti-symmetric part of this coefficient, is always a Poisson structure. Okay? I would be very grateful if you could cite me the source of this, because apparently everybody knows this.
I think there were some, maybe I'm wrong, but some notes. It was a conference 2015 in Würzburg.
Maybe. I know there are some that is appears
Formation quantization stuff.
Yeah. I tried,
But I think it was hard.
but I found that it is suggested as an exercise.
Ah.
I think
when I started-
Francesco D'Andrea should answer this question,
Sorry?
perhaps. Francesco D'Andrea should answer your
Francesco,
question.
please answer. Please.
Sorry, can you repeat?
Repeat the question.
Can you show me the reference for the fact that if you have a one parameter family of associative products on a commutative algebra, on an underlying vector space of a commutative algebra, if this family is differentiable with respect to this one parameter, then the alternated coefficient of the first order term is a Poisson structure.
Yeah, I mean, but this is true for formal deformation, not if
No,
you
no,
have.
no.
No, yeah, I understand the point, but I don't.
Differentiable.
Sorry, if they are?
Differentiable.
If you have a differential with respect to this parameter,
Yeah, but I don't know.
Deformation.
I don't know a reference. I mean, I only know the formal case. I'm not sure. I have no idea. Sorry.
Okay. By the way, what is your reference for this formal case?
Well, any paper or book on deformation quantization, but it's trivial in the formal case. If your product is a formal power series, okay. It still must be differentiable formal deformation. So by the cochain must be differential operators.
Okay.
But that is fine. I mean,
yeah, but is there a proof, or is it this result cited in this article?
which result? Sorry.
This result we are talking about. Even in this formal case.
But he says it's trivial.
Yeah, I think, but maybe I'm wrong. I don't know. I think he's. I mean, I would say that he's well known, but then okay. It is possible that maybe I believe he's well known, but he's not.
Folk knowledge everywhere.
Yeah.
When you are trying to pinpoint the reference for this consultation.
Okay, so Tomek,
maybe refers the strong deformation quantization. Maybe an example, I think.
You mean strict?
Strict deformation. I think so, right.
Yeah, I mean, if it comes from an action
of deformations require topology. This is.
But you said differentiable.
With respect to this parameter. But anyway. Okay. So,
Tomek, sorry, I have another precision since you are very precise here. Commutative multiplication can be even Jordan algebra, for instance, non-associative.
No. Commutative means here associative.
Thank you.
Okay. Official abbreviation for the category of commutative algebras is common. Now, before, Grothendieck proposed COM-ALG, which means nothing. Writing COM-AS would be unpolite. Okay, so let's continue. So we know what is the quasi-classical limit now. It's Poisson limiting structure, first order deformation in a one-parameter family. So this is all a one-parameter family. So one could and should even ask, what about this quasi-classical limit? And the answer is quite interesting, with one exception, one difference compared to this Poisson picture. Instead of an anti-symmetric Poisson bracket, in this quasi-classical limit, we obtain a bracket which is equated symmetric. Okay? It's not a deep mystery. What would be if you have this non-determinate I in our context, what could be it on functions, okay? On elements of 0 degree, it comes from the scalar product of this differential. Since pi is symmetric, it's a symmetric bracket. And since it depends on every argument by the differential, it satisfies this Leibniz property with respect to any argument. Okay, so it is quite close to this Poisson bracket. However, remember, Poisson bracket is first of all anti-symmetric here and satisfies the Jacobi identity. So what about Jacobi identity? Okay, so first of all, we have to define an analog of something which defines Jacobi identity as vanity of something which is called the Jacobiator. Okay? And the Jacobiator vanishing is that this element of this algebra through these brackets acts as a derivation of the bracket itself. Okay? So let's try to take this as the definition of the Jacobiator. If you do not assume anti-symmetry of the bracket, iterates like this. Okay? If you assume that your bracket is anti-symmetric, then you have changed the order of elements here to make this cyclic expression, whose benefit is the Jacobi identity. But if you do not assume anti-symmetry, this is the Jacobian. Okay? And this Jacobian can be applied to any bilinear thing. For instance, to something which is symmetric. Okay? Okay. And then you remember, from Hofstede homological point of view, Levi-Civita connection is the co-boundary, Hofstede co-boundary of the Dirac operator. So it comes from the Dirac operator. Okay? In the limit of this one parameter, plus the limit of this one parameter information, you obtain this symmetric bracket coming from this form, which means that you are reconstructing the matrix. Okay? But where is this Levi-Civita connection? Surprise, the Jacobi. Now, on this level. Okay? It's an astonishing formula because people were playing with the Levi-Civita connection, maybe not for ages, but decades, for many, many decades, almost a century. Okay? And you know this formula expressing this Levi-Civita connection in a way independent of the choice of the coordinate system, without any Christopher symbols. Okay? It was a great achievement. In this, you can ask what is this Levi-Civita connection, for instance, left invariant Levi-Civita connection on the group story. Okay? Without possible formula, it will be very difficult. But nobody asked the question, what is happening when we play with gradients of function and commutators of this gradient? And if you do sufficiently many commutators, what is the result? The result is Jacobi on one hand. On the other hand, it's a Levi-Civita connection again. Okay? The Levi-Civita connection is the right notion from this point of view. So this time, this symmetric analog of the Poisson bracket is primary. And again, Levi-Civita connection is secondary. Okay?
Can you remind me how we get the symmetric bracket here? Okay. Okay.
I'm taking the scalar product of differentials. So for this an analog, maybe not of Poisson situation, it's an analog of the symplectic situation. Because this Poisson thing here, or Poisson analog here, in the symplectic case is invertible. And our pi is invertible. Without pi being invertible, you don't have all this stuff.
Yeah.
Okay? So it is something like
Symplectic.
all the symplectic geometry. And since the Jacobian is not zero, it means that it is not as how to say as geometric from the pointwise point of view as symplectic geometry. Because the deviation, which is related to some parallel transport. Okay? So I try to think about some analogs of this situation in something which is called the homotopy algebra. Okay? When algebraic identities are satisfied up to some higher homotopys. Okay. So I haven't finished this yet. Maybe it's impossible. I don't know. It's a work in progress. But if it is true, it would mean that this Levi-Civita connection is some kind of homology. Okay? Or maybe this parallel transport along the Levi-Civita connection is a kind of homology up to me. This behaves like all Poisson structure. And then, having this defined on functions, since we are deforming not only functions, we are deforming the Rham complex. We could ask, what about extending this bracket to differential forms?
And wait, and I would say this bracket, which bracket is
This bracket, this symmetric bracket.
this one? Okay.
Okay.
Because we have
This
linear bracket.
a limit.
Yeah, but you know, you have K trilinear bracket, symmetric bracket.
This trilinear is not symmetric.
Yeah. But it just wrote this bracket.
Yeah. And then we have the following thing. That there is a unique extension of this bracket from functions to the whole algebra of differential forms. Even more, to all the Rham complex, because this extension is automatically compatible with the differential. How to do this? This extended bracket is uniquely determined on generator of the Rham complex. The generator of functions and differential of functions. Okay? So on functions, it's not simplified. But what is this on pairs when you have a function and a differential? Then it turns that it is symmetric because f is even. Okay? And we have a very nice formula. Look at this. This is the formula for this extension. The same for the bracket between differential. This time it is anti-symmetric and defined by quite similar formula. Okay? And now let's try to understand this from this Poisson analogy point of view. Okay? Imagine that Y is simplectic. What is this? It is zero. In Poisson geometry, this is zero. In simplectic geometry, it is zero. Okay? These are two Hamiltonian vector spaces whose commutator is all Hamiltonian. Okay? And this Hamiltonian corresponds to the anti-symmetric bracket of function with the minus sign. Okay? So, don't put the bracket because this is zero. So it's very interesting because if you try to do similar thing with the geometry, you don't have anything non-trivial. Everything is trivial. But now you have something quite involved. Okay? The same here. What is this thing in symplectic geometry? So this is one. This is the commutator of Hamiltonian fields. This is a Hamiltonian field. Pi inverse of that is the differential of the Hamiltonian. Differential of the differential is zero. So this is again zero. Okay? In symplectic geometry, you have nothing like that. Everything is trivial. So it's a specificity of this symmetric bracket. Because if f and g is symmetric, then look, for such an expression, this is the symmetric part. And this is the anti-symmetric part. Okay? And this has only this anti-symmetric.
So I get 5 minutes.
Okay. Compatibility of the extended bracket with the Rham differential. For instance, this is property of the differential being a derivation of the derivation of the bracket. And this you can check that this holds. But if you have this, then in a routine way, you can prove that this bracket, this extended bracket, induces a greater symmetric bracket under the Rham homology. And then, if your cohomology computes the topology of your, say, derived manifold, okay? There is no place for anything infinitesimal playing a role. And indeed, I checked in some examples that this bracket, in the case of smooth algebraic varieties, in many examples, I do not have a theorem claiming that it is fulfilled always. It is zero. I really hard try to compute some non-trivial, very symmetric bracket on topology forms for some varieties. Always I get zero. But there are some cases related, for instance, to singularities or some kinds of singularities related to singularities of a metric. Okay? Where maybe you can obtain some non-trivial operations coming from the interplay between this bracket and these singularities. Because the Rham homology is a good invariant for smooth things. Okay? If they are not smooth, if your variety is not smooth, then what we are computing is debatable. Okay? So they contain some things which are of transcendental nature, some things which are related to for instance, nilpothoms, if you allow them in your algebra. Sometimes there are things related to singularities. Okay? And then this could provide, I think, an interesting invariant of such singularities in generalized terms. Thank you.
Thank you so much, Tomasz. Okay, are there any questions? Tomasz, do you have any questions yourself?
I have
Okay, Ludwig, Andre, you promised to a ferocious attack at the end of Tomasz.
Yeah, maybe I can start. This will be just a comment that life with torsion will be much more difficult. Okay, Tomek. So using the Dirac operator on a Conlot model, which is the product Cartesian, non-commutative, let's say spectral triple corresponding to the product of a manifold, true manifold, compact manifold with 2 points, Z2. So the algebra C2, two-dimensional complex algebra, we have checked that it has some non-trivial torsion functional. It has non-trivial torsion in our non-commutative torsion in our sense. And then this was the only example we had so far, starting with the zero torsion Dirac operator on the manifold, of course. Yeah. So we motivated by that with Yang Liu and Sugato Mukhopadhyay, we tried to see if it matches this non-commutative torsion, matches in some sense the algebraic torsion, which is defined a la Kohn, okay? Kohn calculus, quotienting by junk forms and blah, 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 the way you went on.
This is what is in Sugato stock, right? In Sugato stock.
That's right. So instead, unfortunately, we could not reproduce this torsion, which we found using the Dirac operator, okay? So it was strange for the reason that this torsion was essentially part of this torsion was landing in junk forms, actually, of course, junk forms, okay? So then we we used two modifications. One due to Goswami and Mukhopadhyay already earlier, that instead of quotienting, you could use the complement of the junk forms in the space of forms. Okay, so since there is a scalar product, the general scalar product. And second thing, a modification due to Mesland and Renyi, a paper which appeared just 2 months ago, probably, or a few months ago. Oh, sorry, half of the last year. In which case they modify substantially. There is not generalization, it's modification. So instead of working with this n forms, so omega, this your forms, okay, also represented as operators using Dirac operator, direct with the tensor product of one forms, okay, so they are there. And then there is another calculus, the differential graded calculus, like con there. And there is a way to define torsion as well. And then composing this and also modifying this torsion we obtained by adding some terms, so since the connections differ by endomorphisms, that we know, okay? So we can modify, we managed finally in the paper which we put just 2 days before last year on the archive. So I suggest, Tomek, have a look there and see which pedestrian approach to this, what you presented today, could be using the torsion, okay? So you have substantially modified your approach with Levi-Civita connection, okay? You should modify this differential grade DJA which we use in order to get something which has a torsion, so to include the torsion. Okay, that's my comment which I wanted to say, okay?
Yeah, thank you, Ludwig.
So can I answer?
It wasn't a question, it was a comment.
It was a comment. Can I comment?
You can comment a comment, but cannot answer.
Okay. So my first answer or comment would be like this of Laplace given to Napoleon.
So I have to say it in French.
I have to assume this hypothesis. Okay? There is no natural place where here any kind of torsion appears. Only Levi-Civita connection appears in a natural manner. So when you try to change this by putting by hand some other connection, which is metric, but with torsion, it will be a completely different story. Because it would depend on some additional data. For instance, in this Mesland-Renyi, and maybe also Södergaard approach, they are also talking about junk forms, but their junk forms are not in different algebras, in fact. They are in the tensor algebra of differential forms, one forms. Okay? Then they are taking some projection, which means some decomposition, mimicking the decomposition of two tensors into the sum of the symmetric tensor and anti-symmetric tensor. And they are talking about the connection, in fact, which is induced by this splitting. Okay?
Okay.
So it's hard to compare these approaches because their approaches how to mimic what we love from the classical geometry in terms of connections and so on and so forth. And this gives you more flexibility, especially in the non-commutative case, because this projection splitting into something being an analog of the symmetric and something being analog of the anti-symmetric part is not canonical. So you can, using non-commutativity, you can move it. Okay? So the difference between these approaches and my approach is that my approach is completely canonical.
Okay.
The only datum I started with is this non-degenerate symmetric form.
The beginning of everything.
Yeah.
Okay, so let me add another comment. 3 days, last 3 days before the end, last year, we put a paper also with Arek Bochniak, Andrzej Sitarz, and Paweł Zalecki, in which the title is An Impediment for Torsion from Spectral Geometry. Okay, so it's along your lines. Okay, thank you.
I will have it.
I see Andrzej getting ready for a strike. No, okay. Anybody else? Francesco?
No, maybe I have just a question about the picture.
Yeah, is it from Wilanów?
Yes.
Yes, it's from Wilanów.
Okay,
Garden
thanks.
Right.
Yes.
Wilanów in Warsaw.
No, I strongly recommend you see it. It's very cool.
It was the first seminar in its calendar year.
Yeah.
I found it
Very good. Okay, Jan, you have a question? Yes.
Yes. So Tomasz, so here you only use this algebraic structure, right? So you don't want to involve any like analytic part, because I mean when I look at this brackets, I think it's closely related to they call it deletion forms in this sort of more analytic.
What? Sorry.
So I think these symmetric brackets, it's after this integration it's the deletion form, they call the deletion form. I mean in this analytic context, I think this algebraic property is also has a lot of the literature like in this analytic context. I think probably so here you only talk about algebraic, right? You only use this algebraic structure, not any analytic part.
Yes, yes.
So
adding analysis or even functional analysis here would be modeling
The waters.
Yeah.
okay. So another question is, I was just curious about this picture. So okay, so when you have this classical context, like if I take the example of manifolds, like Riemannian manifolds with a Levi-Chivita connection, I can understand all these algebraic properties that you put. So, but I think the point is do something opposite, right? So you want to use some other algebraic properties to really recover this so say Levi-Chivita connection or Dirac operators, right? So it's what's the big picture, or what's the purpose? Like
I try to not answer, but check whether I understood your talk correctly. For me, the take-home message from Tomasz's talk is that yes, you have a certain hands-on concrete construction of a Dirac operator from a Levi-Civita connection, and then you kind of reverse these formulas. It's like Copernican transformation. You say, aha, so it's not the sun which is rotating around the Earth, it's the Earth which is rotating. Like not good geometry. You just reverse the center of gravity, And when you say, yeah, okay, so now with this specifically constructed Dirac operator via Levi-Civita connection, I can now write a formula. I can have this beta Cauchy cocycle, and now I can say, aha, the Levi-Civita connection can be uniquely determined by any of these Dirac operators which satisfy some properties. And now this is in the spirit of Alan Kohn. It's the Dirac which is at the center of gravity. That's how I understand your.
Yes. It was my intention.
Yeah.
Oh, I started in this analogy with spectral theory of spectral triples. So it's in a sense it's a quasi, or maybe no, it's a kind of shadow, algebraic shadow of spectral geometry of Alan Kohn.
Yeah, I like this.
Okay.
Mm-hmm.
Algebraic.
Yeah.
All these questions here are so algebraic, then I can apply them to quite different situations. Why not to take, for instance, some singular algebraic varieties? What about algebraic varieties having nilpotence? All these calculus go through.
Mm-hmm.
What about schemes which are finite dimensional? Or For instance, the algebra of functions would be like truncated polynomials, which means that these are multiple points, like points who collided, making, for instance, a double point. There is an interesting differential geometry again behind this situation, which could be analyzed through this language.
Okay, so for example, like in the case of so you assume this algebra is from some smooth variety, right?
Not necessarily.
So okay, so if
I need smooth varieties, to have this interplay between the Dirac operator and Levi-Civita connection.
yes, so yes, without the smoothness, I don't know how to define this nabla.
It turns out that if you have this the Rham calculus, you can obtain the same de Rham calculus from different Dirac operators. Okay?
Different.
It means that although these degenerate spaces have a single classical geometry, then they can be limits of different quantizations, in a sense. Okay? I can take all these theorems about this relationship between the Dirac operator and this Levi-Civita connection metric, and I can find solutions to these equations. If you remember, this Dirac operator producing a given Levi-Civita connection is not unique. It's known only up to some one cocycle. So adding this one cocycle, I'm modifying this, let's say, quantization. Okay? And
with the same quasi.
and the Dirac operator of this, for instance, quantizations of this, even for the case of a double point, when the algebra of functions is non-trivial. It's an algebra of truncated polynomials. It's k extended by t divided by t squared. This is a very simple thing. But already in this situation, you can classify all the Dirac operators even to the classical de Rham structure in the limit. And you can compute the spectrum of this. And this spectrum is quite interesting, depending on the parameter of the deformation. You have three values in the spectrum. One positive, maybe not positive, 1, 0, and 2 outside 0. Okay?
Yes, okay. For example, like when you talk about Dirac operator, I mean,
so these are Dirac operators in very exotic situations, like
yes. So it's like you always use a connection to define a Dirac operator, right? So do you have an example like you use the Dirac operator somehow like without the connection, so then somehow you can reproduce.
Yes. I told you. I took the double point and I classified all possible Dirac operators, realizing the classical de Rham calculus on this double point.
Then what's okay? So then what's the algebraic property about this Dirac operator? What are the algebraic properties required to call it a Dirac operator? So in this.
So first, okay. So this is a cochain, Hochschild cochain, whose coboundary is a Levi-Civita connection of the quasi-classical limit.
And then you
of functions.
So
this could be an axiom. This could be an axiom. So these theorems could be made axioms of some analog of spectral geometry, when instead of Hilbert spaces, you are playing with some algebras which are mimicking the Clifford-Dirac. And you have the Dirac operator, you have some Hochschild cochain satisfying this Hochschild cohomological and this quasi-classical limit condition.
Yes. Okay. So in your definition, you involve something like Levitshev. I mean, for example, like in a case of like a singular like varieties, does it have a notion of Levitshev? I mean, this.
I don't understand.
So
I have to read your mouth because now I hear only echo.
okay. So now can you hear me clearly? So yeah.
Yeah.
But
So
the question
I think
was,
so when
Tomek, the
you
question, yes, the question was if you have Levi-Civita on singular manifold, for instance.
Yeah, but what is Levi-Civita on singular manifold?
That's the question to you.
Outside
That's the question.
singularities, you can speak about Levi-Civita. Okay, so in the algebraic case, singularities are always single. So regular points form something which is open and dense. Okay?
oh
And to say that you have singularity, you can say, okay, you have some stratification with some smooth regular strata, okay? And this stratification satisfies some compatibilities. You can define some metric, Riemann metric, Riemann metric on every stratum, and then kind of compatibility when you are going from one stratum to another defines a kind of metric singularity. Okay. So this is very general language. You can fill it with many concrete situations and try to classify all possible Dirac operators, which mean quantizations, okay, of a given classical geometry of singular spaces.
yes. So okay. So my question is very simple. So when you mentioned Dirac operators, right? So in your definition, you always used some Levitshev or some metric or something, right? So it's I don't understand. So what's the precise definition of Dirac operators? Like you want to
but you missed the most important thing. At some moment, the Dirac operator was producing all other structures from which it was produced. Okay? So you can start from the Dirac, satisfying some conditions.
And I guess it's asking what these conditions are.
Yeah, what are the conditions? That's I'm curious.
I told you. So first of all, okay. So on an open strata, when you have this regular situation, this should give you this situation I was talking about. If you have these singularities, then you can speak about this Dirac operator whose open boundary satisfies on every smooth stratum the condition of being the Levi-Civita connection of the quasi-classical limit of this quantization, which is this metric.
Okay, so then this Levitshev connection get involved.
So this is classic. So this is being Dirac means being a quantization of the classical situation. I always have to refer to the classical situation. It is a quantization of the Rham complex.
Okay.
Of course, you can abstract it to the situation when you have very abstract ascending filtered Z2 graded algebra with some abstract operator. Okay. And then you can mimic the spectral geometry of Kohn, with some conditions, allowing you to speak completely abstract about your situation. So when you are trying to quantize or construct completely non-commutative version of this, you should construct an environment in which you can see this classical phenomena I was talking about today. The spectral geometry, according to Alain Don, is very general. It's too general to give you in this classical situation all the structures outside of this smooth situation. So we need if you understand the lesson of deformation quantization, okay? Before we start constructing strict quantization, we have to go through this formal deformation quantization. We have to start from some Poisson structure, okay? And then we know what we are quantizing. If we don't have this semi-classical limit, if we don't have this Riemannian geometry, we started in this quantization, okay? Then we are on the very abstract level when very little can be said in any contact with interesting mathematics. Because it's topology, there's no topology here. There are no functional analysis, pure algebra. So if you axiomatize the situation on this, on the most general algebraic level, it takes something empty. Only the contact with the classical mathematics makes it a little more safe.
Yeah, I like it. This is why we were talking about flirtations.
Yes.
Flirtations are usually said.
Semi-flirtation.
Okay, so if there are no other questions, you guys have some other questions?
So you about quantization, and you have this analog of Poisson brackets, like a symplectic form. But what would be the quantum analog of that? The quantum analog of that, of these brackets?
This bracket is a Poisson bracket,
yeah,
without any extension to differential forms.
Okay.
In symplectic geometry, you don't have any extension, not trivial extension. This higher bracket are zero. Of course, I know there is a big business around extending the Poisson structure to differential forms. And there are many competing ways of doing this. Generalizing partially some separate aspects of the Poisson structure. Okay?
Okay.
You have the version of Grabowski, you have the version of many people, many other people.
Okay. And also, you mentioned maybe 3 slides back.
Can you go back 3 slides?
There are 2. So one forward.
Forward?
Yes. Like these 2 equations that in the classical setting, they are 0. I mean, you have like like setting like look like equations of motion or something. But do you have? Can you speak at least at the philosophical level for these kinds of things?
On the philosophical level, it's not about motion like in the case of Hamiltonian motion.
Yeah.
It is rather like in wave dynamics, because we are talking about gradients. So the propagation, which is behind this story, is a propagation along the gradient of some objects which are like functions. Okay?
Mm-hmm.
So what is special in the Hamiltonian dynamics? That if you have a Hamiltonian, then the Hamiltonian field is tangent to the level set of this Hamiltonian.
Mm-hmm.
Okay? But here, this gradient is orthogonal to the level set of this function. So this is a completely different story. So this is like the story of Hamiltonian dynamics Okay? So Hamiltonian dynamics is like this. You have a level set of some function f equal constants. Okay? And then you have a trajectory of the Hamiltonian field of this function. So this is geometry behind the Hamiltonian mechanism. Okay? Here we have functions. Okay? But the flow is perpendicular to your level set. So the story is quite different. It's not about some particles moving in some space. It's like some waves propagating in a space in the direction of this race. Okay?
Okay.
So you can say that this is some wave equivalent of this particle.
Right.
Okay.
Yeah.
Okay. If there are no other urgent questions, I suggest we thank our speaker again for a very intriguing talk. Thank you so much. Stop recording.